Hey, welcome! Do you ever feel like every graph you see in math class is a brand new, impossible puzzle? Well, what if I told you that most of them are really just different versions of a few simple, original graphs? Today, we're going to crack the code on parent functions. Seriously, this is like the master key to understanding graphs in algebra.
Okay, let's just jump right in with a question. Look at these two functions, y equals x squared and y equals x minus 3 squared. They look almost the same, right? But that little minus 3 in there makes a big difference. The crazy part, they are absolutely from the same family. Let's figure out how that's even possible.
So here's our game plan. First, we're going to tackle this wild idea of function families. Then we'll meet the original, the parent, if you will. We'll walk through a real example to see it in action. Then check out how these same rules apply to other functions. We'll even learn how to work backward, starting with just data. And you're going to want to stick around to the end, because we'll show you how all of this becomes your new favorite math shortcut.
Yeah, you heard that right. Functions totally have families. Just like people, you can group them together based on their core structure and what they have in common. That connection between y equals x squared and y equals x minus 3 squared, well, it's not a coincidence. It's a family resemblance.
And in any family tree, you've got that one common ancestor, right? The starting point where everyone else comes from. In the world of functions, we call that the parent function. It really is like a family tree, but for graphs. You can have all these complicated, unique-looking functions, but you can always trace them back to one simple original ancestor. And that ancestor, it holds all the core DNA, the basic shape and behavior of the entire family. So here's the official idea. A parent function is the most basic, stripped-down version in its family. Every other function you run into is just a transformation, a modified version of that parent. You can think of it like the original blueprint. Everything else is just a tweak on that first design.
Okay, enough theory. Let's make this real by diving into our first example. Seeing it happen is way better than just talking about it.
All right, let's put them side by side. Over on the left, we've got our parent, the simple quadratic function, f of x equals x squared. And on the right, we have its child function. Look closely. The only thing that's different is that minus 3, tucked right inside the parentheses. That tiny change is the whole key to what's going on here.
So first, let's get our bearings. The graph of our parent function, x squared, is that classic U shape, a parabola. Its most important point, the vertex, is sitting right at the origin, at 0, 0. That's our home base. Now, look what happens to our new function. That minus 3 in the equation didn't change the U shape at all. All it did was pick the entire graph up and move it. That key point isn't at 0, 0 anymore. Now it's over at 3, 0. So here's a simple 3-step playbook you can use every time. Step 1, figure out the parent. That little exponent of 2 tells us it's in the quadratic family. Step 2, see what's changed. The key point moved from 0, 0 to 3, 0. And step 3, describe that change. It's just a horizontal slide or translation 3 units to the right. And that's it, you've cracked the code. Okay, now that we've got the hang of parabolas, let's zoom out a bit. This whole idea doesn't just work for quadratics, it works for tons of function families. And the first step is always the same. You gotta spot the parent. Let's do a little quick fire round here. Look at g of x equals x minus 1 cubed. What's the main thing happening? Cubing. So the parent is x cubed. What about x plus 1 squared? The main operation is squaring, so the parent is x squared. The square root of x plus 3, the parent is just the square root of x. See the pattern? To find the parent, you just strip away all the extra numbers being added or subtracted to get back to the simplest version. All right, but what happens if you don't even have the equation? What if all you've got is a table of numbers? Well, we can actually work backward from the data to figure out which family it belongs to. Take a look at this data set. We've got our x values and the y values that go with them. Your job now is to be a detective. What's the mathematical rule that's connecting every single x to its y?
Look really closely at the clues here. When x is negative 3, y is negative 27. When x is a positive 3, y is a positive 27. What simple operation links those numbers together? I'll give you a second to think about it.
And if you guessed the cubic function, you are absolutely right. Every y value is just its x value cubed. Negative 3 times negative 3 times negative 3 gives you negative 27.
The data is a perfect match for the parent function f of x equals x cubed.
So why does any of this matter? Why have we spent all this time on function families? Well, because understanding parent functions isn't just some neat trick. It is a massive shortcut to understanding how graphs work on a much deeper level.
Let's boil it all down. This is really about working smarter, not harder. Instead of trying to memorize hundreds of different graphs, you only need to know a handful of parents. Once you can recognize them, you can instantly predict the shape and behavior of any graph in their family. It basically turns graphing from this tedious job of plotting a million points into a simple game of spot the parent and see how it moved.
So we've pretty much mastered how to slide functions around a graph, left, right, up, down. But what if we want to actually change their shape? Our final question is this. What happens when we don't just add or subtract, but we start multiplying? How can we stretch or shrink or even flip a function's graph completely upside down? That, my friends, is the next layer of the code.